Welcome guys. Yeah, so today we start a new topic about mathematical analysis. Yeah, so basically follow the routine or apostle. And previously I already talked about basic topology, and I think all the things you need to know, except for idea called connected set. Yeah, and maybe we'll talk in the future. So I will post the link below if you want to know about basic topology. And my channel most do the advanced mathematics and yeah, I mean whatever, right? So yeah, see you guys. Yeah, so not see you guys. Yeah. Okay, so hope you guys subscribe to my channel. Okay, so basically just follow a routine or apostle. Okay, so it's my yeah, maybe I spell wrong. Okay. Yeah, so today topic is a series. Okay, so maybe 5 or 6 video will finish this. Okay, so definition. So let's talk about a converge of C series. Okay. So definition is that we start from a matrix space, and we take series. Right? So n from 1 to infinity, some Pn, each Pn is inside X. And for epsilon greater than 0, there's an integer n such that when n greater than n, so this small n greater than n, we have Pn minus some points, let's say x zeros, the absolute value, or somehow people use a distance less than epsilon, and we say the Pn converge to x zeros. Okay, so what I'm saying is that you pick up arrow, you have Pn, right? This is P2, P3, and keep going. And then you set a number called x zeros, and then you for epsilon greater than zeros, you can find if you can find when n large enough, and it will arbitrarily close to x zeros, then this is called converge. Okay, and the distance is based on your metric space. Okay. Okay, so quick example, 1 over n squared. Actually, I don't want to talk about examples because I think this is trivial idea, but we can still talk a little bit. Okay. Yeah, so this is 1. So let's see, this is converge, right? Converge to zeros, and then these guys diverge, right? Become infinity. Oh, by the way, so the definition is that if Pn do not converge, then it diverge. Definition. Okay. Well, how about this, right? So when n goes to infinity, this term goes to 0, right? So as n close to 1, converge to 1. And what about this in, right? So you can check when n equals, you can check that it's basically a cyclic group. So you say I and I squared, which is -1, I cube is minus I to the 4 is 1, right? So it's a cyclic group with order 4. So isomorph the z to the 4, right? Z to the -4z. So it's not converge, right? Because it's basically jumping from this. Okay, so yeah, converge 1. Okay. Okay, so theorem, you should remember. So let's say Pn is a sequence of x. Okay, so I think the following are equivalent. Okay, so the first one is that Pn converge to P belongs to x, x if and only if so every neighborhood and BHD of B contains Pn for all but finitely many Pn. Okay, so B says that sorry, not the following equivalent. I should say the following is true. Okay, so the following is true. So Pn approach to P, and then P is unique. So there's a series only converge to one number, not two number. Okay, see, Pn converge, and then Pn is bounded. So bounded means that there's m such that the Pn cannot greater than m, right, for all n. D. If V is a subset x, and the P is a limit, point of E, then there is a Pn such that the Pn in E such that Pn converge to P. Okay, so this theorem, these four theorems tell you the limit point in the topology and the relationship with sequence. Okay. Okay, so let's prove the first one. So first one says what? Says that so let's say Pn converge to P, and then you take the neighborhood. Let's say that V is a neighborhood of the P, right? And so that means for epsilon greater than zeros, right? You can find a dqp less than 0, right? For some q in Pn. Wait, sorry. So let's take an open neighborhood of V, right? So I can take the V to be open ball, right? So let's take the epsilon to be let's take V to be the ball with the radius epsilon, right? So that means for any let's say so what I'm trying to prove is what every neighborhood of P contains Pn, right? So right, this is P, right? This is V, right? So it's open, so I can find a ball with radius epsilon such that if any points with the radius dpq less epsilon will inside V, right? But by definition, for n, I can find n, right? I can find such n when n large enough. You can find another point here. Let's say this is q prime, right? So q prime is a subset. Q prime belongs to a series, right? So such that q prime sit in V, right? So q prime is in V because V cover P, and I can find some point which is very close to P. Okay, so yeah, so this is just the proof. Okay, so yeah, done. Okay. So I prove this direction. I prove this direction. I say in every neighborhood of P contains Pn for all, right? But finite in many Pn. Okay, so let's say conversely. So conversely. So let's say every neighborhood of P contains all but finitely many Pn. That means for epsilon greater than 0, let's say V be a set of all. Let's say V be a set of all Q belongs to X such that dpq less than epsilon. By assumption, right? By assumption, right? By assumption that every neighborhood of P contains Pn for all but finitely many Pn, right? So that means you can find n, large n, right? Such that Pn belongs to V for n greater or equal to n, right? So that means d, P, and P less than epsilon if n greater or equal to n, right? By this property. Okay. Right, but you read the words, it's just Pn converge to P, right? So basically, the first A just the restatement. Okay. So B, if Pn converge to P, and P is unique. Okay, I think this is trivial because you can see this. So suppose that Pn converge to P and Pn converge to P prime. Okay, we want to prove it's the same, right? But so you know that for epsilon greater than 0, right? You can find n. Let's say this is called n1, right? Such that when n greater or equal to n1, then your dp and p can be less than epsilon, right? And then let's say this is n2, such that n greater or equal to n2, where dp and p prime can be less than epsilon, right? But your dp and p prime will less than dp and p plus the p and p prime, right? So this is epsilon plus epsilon, which is 2 epsilon. Right? So take epsilon to be arbitrarily small. So that means the distance of these 2 points must be arbitrarily small, right? So the only possibility is that dpp prime is greater than 0, right? By the property of the metric space, they must be the same points. Okay. C. Okay, so Cn is Pn is a converge, and Pn is bounded. I think this is very at the I mean the elementary analysis. So I think this is also should be viewed as exercise. Okay, so Yeah, so you know that, right? Find epsilon greater than 0, you find n greater than, let's say you find n, right? And when n greater than n, your dp and p less than epsilon, right? So that means for n greater than n, your dp and p is already bounded by epsilon, right? Be close to p. So let's say your, so this is p, right? This is epsilon. So all the points n greater than larger n is already seen inside here. Okay, so if you start from zeros, I can say what? I can, and I pick the rest point as a, this is P1, P2, up to Pn minus 1. Right, so I can set all the Pn sets, right? All the points in these Pn sets. At most has distance with maximum of, let's say, P1, P2, up to Pn minus 1. And also, so the largest is from this P to epsilon, right? So it's dP epsilon. Sorry, this is the distance with P. So this different. Yeah, this is dP0 and plus epsilon, right? So all the points with greater n greater or equal to large n is basically constrained by this matrix space. Constraint in this large ball, right? And the rest are just finite points. So all these are all just finite number, right? So maximum is finite, so it's bounded, right? So okay, yeah. So D, so E subset of X, and the P is a limit point of E. Then there's a sequence, so P is a limit point of E. Then you can find a sequence Pn, right, of E such that Pn converge to E from P. Yeah, so this is trivial. Okay, by definition, what's a limit point? Limit point, let's say it's P. The limit point means that for any epsilon, right? So for any epsilon greater than 0, right? There's you can find a point which is not P, right, but inside E. Okay. So let's pick up epsilon to be 1 over n, right? So you can find Pn, right? Such that so you can find Pn such that the distance between Pn and P are less than 1 over n, right, for each n. This is the property of the limit point. Okay, so obviously from here, you know that for epsilon greater than 0, once you choose n is large enough, this 1 over n will less than epsilon, right? So by definition, Pn converge to P. Okay, and by definition, it's the limit point of E, so each Pn is inside E. So this is somehow like just restatement. Okay, so there's a theorem that I will post the proof link below because I already proved this in my other videos. So I don't want to prove. So suppose suppose you have these two. Oh, by the way, so from now on, when Sn converges to S, I somehow return at least two. Okay. So let's assume that all of these are complex series. Okay, so then you have the famous four results. Let's say Sn plus Tn when n goes to infinity converge to S plus T. Okay, and the Sn Tn is T, Sn minus Tn converge to S minus T, and Sn divided Tn converge to S divided by T if T is not 0 and all n are non-zero, Tn are non-zero. Okay, so this is just from a proof, just from definition. I will post the link. I will post the link below. Okay, so should be exercise. I think this is almost trivial. Okay, so except for these two are trivial, right? B minus is S plus. Don't worry, I will post the proof link below. Okay. Okay, so finally a quick generalization theorem. So suppose that you have a multi-dimension like the Euclidean space. So let's say Xn is Rk. So each n contains k tuples, right? For example, x1 contains let's say x1 contains let's say alpha 1 alpha 1 2 up to alpha 1 n, right? 1k, right? And this alpha ij are basically from all a complex number, and x2 do the same thing, alpha to 1, alpha to 2, alpha to k, right? So these are all complex number. Okay, so I can talk about xn, right? I can say xn converge if and only if. So theorem says that xn converge. So converge in the sense of the Euclidean space as long as each component converge. So each component converge, right, as R. So that means if this alpha big notation like alpha I converge, alpha I1 converge, and alpha I2 converge. Yeah, so basically each small component converge will imply the tuple component converge. If the tuple converge, it means that each component converge. Okay. So proof, just bounded, yeah, just try to use one to bound another. So bound another. So key idea is that bound another. Okay, so let's assume that let's see what if this coverage will imply, right? So this coverage will imply that for all epsilon greater than 0, right? You can find the n, right? So when n greater larger than n, your xn minus some points is x zeros, right? Well less than epsilon, right? So, but this is just the Euclidean space, right? So it just summates alpha. Right, so this is just some like alpha n, let's say alpha n I, right, minus let's say x zeros. So let's say x zeros is just maybe p1 or p2 up to pk. Okay, so it's let's say p I, right? So I from 1 to k. That's the epsilon, right? But you see that since all these are square number less than epsilon, that means you can quickly get that alpha ni minus pi, right? Will convert well less than epsilon, right? For each I, right? So from this you get this, right? This is very crude, but obviously true because this is all square. Okay, so all positive. So that means you read the words for epsilon greater than zeros. There is this n such that n greater than n. This is less than epsilon, right? So you prove that each component converge. Okay. Conversely, yeah, so I don't want to write. Conversely, if everyone is less than can be controlled, then your sum square can be controlled. Okay, so done. Okay, yeah, and let's see what I can say. Okay, so next time we talk about subsequence and Cauchy sequence. See you guys next videos.